All right. So this rumor, detection, rumor propagation model, we have seen that there are 4 states: S, I, E, and Z, right? And these are different probabilities, right? Different probabilities based on which the population moves from one state to another state, right? So in this particular research, the authors, proposed something called the flux ratio. Okay. Now, what is this flux ratio? The flux ratio is essentially, indicating the fraction of users, right? Fraction of users who are actually moving from the exposed states to the infected states. Okay, so there are 2 quantities. One quantity is the number of exposed users, right? And what do you mean by an exposed user? An exposed user is essentially a user who is who has already encountered the rumor, for example, or who has already encountered the disease, right? So since this is about rumor propagation, assume that exposed users are those users who have already encountered the rumor, right? And you see here that with certain probability, some of the users are moving to some of the exposed users are moving to infected, meaning that those users will further retweet the rumor. Okay, so when somebody retweets a rumor, we will assume that that guy has already the guy has already got infected by the rumor. Okay, so flux ratio is basically the influx is the ratio of influx by outflux, right, with respect to the state exposed. Okay, so if you look at the quantity here, it is basically saying that the influx, which is the numerator, is basically beta times 1 minus p plus b times 1 minus l, right? This is the influx, and outflux is this plus this, right? Now you may ask, what is this epsilon? Epsilon is just a kind of an error parameter or whatever, tuning parameter that we generally use to feed the data points with the feed the model with the data points, right? So you see, this is influx and this is outflux. Okay, so now let's try to understand the meaning of this flux ratio. So the higher the flux ratio, meaning higher the numerator, that will indicate that that say if the flux ratio is much higher than 1, that would indicate that a lot of people have been exposed, but there are small number of people who have actually got infected, right? If it is higher, then this would be higher. So exposed users are much higher than the number of infected users. And if it is 1, or if it is less than 1, right, then it basically indicates that this number is much lesser than this number. Okay, so what the author they have done, they have essentially taken data from real world, and they have actually considered a few real event and few rumor event. For example, real event, they considered Boston Marathon exposure, then some Pope's resignation, right? Michelle Obama, some Oscar party, and so on and so forth. Whereas rumor, they consider Obama injured, right? Fidel Castro's coming death. These are all rumors, right? Some riots and shooting in Mexico. They collected data from social media related to real events and related to rumors. Okay, and then for every event, they plotted this flux ratio. Okay, so if you look at here, this green bars correspond to real events, and red bars correspond to fake events. Okay, and x-axis is the event, and y-axis is the flux ratio. So if you see here, all 3 green bars, okay, there are 4 real world events except this one. All other 3 real events, right, which are not fake, all 3 real events have flux ratio greater than 1. In fact, you see the ratio is much greater than 1. The first one is 28, second one is 24, and so on. Whereas for all the fake events, the flux ratio is less than 1. Okay, 0.25, 0.2, 0.1. So these are all fake events and these are all real events. Okay, what does it mean? So it means that real news, right? Real news. So people are exposed to the real news much higher than converting from exposed to infected, right? So people believe about the people are exposed to the real event, but they would not share the real events. Whereas if you look at the fake events, right, the denominator is higher, right? Meaning there are a significant number of users who were also infected, right, compared to the exposed state. So and this is the real reason behind the massive spread of rumor, fake news, and so on, right? People tend to retweet rumors much higher than the tendency of retweeting a rumor or a fake news is higher than the tendency of retweeting a real news. Okay, and this again further confirms the the phenomenon like echo chamber, the phenomenon like conformity bias, and so on and so forth. Say within an echo chamber, if you see that people of your neighbors are sharing certain information and you are already biased towards that topic, right, or that political party, you'd further retweet that information as well, right? And this is the idea. In fact, it is also interesting to see that is this happening because of the social pressure or because of the natural tendency. So you can further plot for every data point, right? You can further see whether the majority of the users neighbors, right? You take a user and you look at all the neighbors of that user, and if you try to understand that, okay, if majority of the neighbors are infected, then you get infected, or if if at least one neighbor is infected, you will get infected. Is it because of the social pressure or is it because of the natural choice? Okay, so now let's move to the next model, which is again a basic model, but people generally use this model quite often for as a baseline these days, as a baseline for say rumor propagation or fake news propagation or any information diffusion in general. This model is called independent cascade model or IC model. Okay, so what we have seen so far, we have seen deterministic process where user takes the user chooses a certain decision, certain strategy deterministically, right, based on the neighbors effect, right? The neighbors and in fact the decision is actually determined by the payoff, right? We have seen that kind of model. We have also seen probabilistic models like SIR, SIS, where with certain probability susceptible node gets infected, certain probability the infected node gets recovered, and so on and so forth, right? And we have seen that those probabilities, say beta, gamma, right, birth rate, death rate, we have discussed so far. So these probabilities are constant for a particular setting, right? It is not dependent on the user, or it is not dependent on the network, for example, right? So and you can tune these parameters to fit the data points well. Now here we will discuss something different, although this is also a probabilistic model, but the concept is a little bit different from SIR, SIS type models. So this is called IC model or independent cascade model, right? What is the idea? The idea is very simple. So here we assign a probability to every edge, right? For example, if there's an edge from B to A, and let's assume that it's a directed network like follower type network. If there is an edge from B to A, right? So, and let's assume that the probability is 0.4. What is this probability? This probability is basically, the probability is the infection probability. Okay. And you see that these probabilities are different for different ages. Unlike SIS type models, here the probabilities are different. And every age is associated with a probability, and that is independent of the other probabilities. Therefore, this is called independent cascade model. Why this is called independent cascade? Because when a cascade grows from one node to another node to another node, it is independent of the growth of the other cascade. Okay, so let's try to understand. Let's start from A, for example. Okay, and you see that with probability 0.4, A will infect D. With probability 0.2, A will infect E. With probability 0.3, A will infect F. Note that it is not necessary that the sum of the probabilities of all the outgoing edges is 1. It is not necessary. And these probabilities are dependent on the situation, dependent on the setting, dependent on how users want to model. Okay. So how does it, let's assume that you know all these probabilities. Let us assume that you know all the probabilities associated with edges, right? And how do you then grow a particular cascade? So let's say you start from A, right? And you choose this edge, okay, this edge. You toss a coin, right? You toss a coin with probability P. Say you have a threshold, right? Say the threshold is 0.4, right? And you toss a coin. If say the outcome is 0.3, for example, you will not infect T. If it is greater than 0.4, then A will infect D. Similarly, you choose this edge, toss a coin, a biased coin. Remember, this is a biased coin because these probabilities are not uniform. And if it is greater than the threshold, right, then A will infect T, otherwise not. Similarly here, right? And let's assume that according to your coin toss, A has infected E and F, but A has not infected D. Okay, so E and F have been infected by A. Then again, you start from A. Okay, you choose each of its outgoing edges, this one and this one, independently, and toss coins, and you decide whether to infect the next one. And remember, since F has already been infected, there is no point in choosing this edge. There is no point in choosing this edge. Okay, so it basically activates each of the out neighbors, right, with some probability PUV, right? Now think about it. So the first question will automatically arise is that how do you identify these edges? How do you identify these probabilities associated with edges? Right? So many probabilities, number of edges if order of P, so you have to compute order of E probabilities. How do you compute it? I mean, one can argue that, hey, if you have some historical data or some other information, you can do that. Some prior, you can do that, but this is not a realistic setting per se, right? So people may argue that, okay, it is understood that probabilities of all these edges computation is difficult. So the simplest assumption is that let's assume that all the probabilities are same, right? Make all edges have same weight, same probability. If you do that, then this is same as SIR model, right? If you do that, then this would be same as SIR model, with a little difference that in SIS kind of models I have mentioned, right, is that we assume that it's a perfect mixing, meaning all the nodes are connected to all the nodes, right? But here, as you see, here we consider a topology, a network topology, right? Although we are considering a network topology, if you consider all the edges with equal probability, then this would be too simple model, and there will be very little difference between SIS kind of model and the IC model, right? So the question is, can we do better? So what people suggested is something called exposure adaptation model, right? And this is very same as the previous concept, but little different. So exposure adaptation concept, the idea is that let's take a user, right? Let's take this user, and this user has so many neighbors, right? And assume that some fraction of neighbors have already been infected, right? So the meaning that this user has already been exposed to that user, right? With this user has already been exposed to the disease or rheum or whatever, right? And then with certain probability, the node will get infected. So what's the difference here? The difference is that now we are moving from edge-centric probability to node-centric probability. Okay, what we are saying? We are saying that a node will, with certain probability, a node will decide whether it will adapt to a particular strategy, it will adapt to a particular behavior, particular humor or not. Okay, so now, so what is interesting here is that if you think of this kind of models, right, that depending upon the user's neighbor's behavior, a particular node will adapt a particular strategy or not. So if you try to understand this kind of behavior, right, what you need to do, you need to draw something called exposure curve, right? What is exposure curve? Exposure curve is a probability of adapting a new behavior. It basically says that what is the probability of a node adapting a new behavior depending upon the number of friends who have already adapted the strategy. Okay, so think about it. So let's assume this curve. Okay, x-axis is the number of friends who have already adapted. We have already adapted a particular rumor, for example, right? And the y-axis says that what is the probability that you will also adapt this particular information. Okay, if you think of a probabilistic model, each node has a probability, right? You will see this kind of exposure curve. You see the exposure curve here. So this exposure curve is basically indicating that your model is a probabilistic model. On the other hand, if it is a decision-making model, the one that we discussed at the beginning, right, the same exposure curve would look like this, a kind of an S-shaped curve. What does it indicate? It indicates that, if less number of neighbors are infected, you will not adapt. It is less likely that you will adapt to a particular strategy or humor, right? As the number grows after a certain threshold, this probability will increase significantly. And this is very different from the probabilistic model. Okay. In fact, exposure curve, right? There, in fact, this depending upon the strategy or depending upon the settings, you can have different types of exposure curves. For example, if you see that your exposure curve looks like this, right? Initially, so x-axis is the number of exposures and y-axis is the number of infection, meaning adoption, right? You see, you can have this kind of curve, increasing and then decay. What does it mean? It means that with little exposure, it will infect significantly. And then as the exposure grows, it will decay. Right? You can think of it as a super, a kind of a virus which is super spreader. Right? So you see that, okay, if at least one of your neighbors is infected, you will also get infected. Right? So this can be one setting. Other setting can be like this, right? As I already mentioned, exposure versus infected. You see that with the increase of exposure, the infection probability will increase gradually, right? Or you can see, in fact, this kind of curve where with the increase of exposure, it is decreasing. So it meaning that at the initial stage, you have maximum infection, right? And then it is decreasing. So you can think of this as a shifted version of this curve. left shifted version of this curve, right? Meaning that with very, very little exposure, you will get infected, and then after a certain point in time, you are now resistant, right? You are immune, and then you will not get infected further. So it will decrease over time. Okay. So exposure curves are very important. Now, so let's think of another setting, right? So far we have seen disease spreading, we have seen rumor spreading. Now think of something called viral marketing. So in viral marketing, one particular setting is, let's say, in e-commerce service, there is something called referral. We all know what is referral, right? Basically, it says that, okay, if you refer this product to somebody, right, or if you influence somebody to subscribe to certain channel or certain a certain scheme, right, you will get this amount of credit, and whosoever has subscribed, he or she will also get the equal amount of credit. Referral service, and referral service is everywhere. This is an example of viral marketing, right? So you see here that, okay, if you influence this lady to buy this book, you will get a 10% credit, and that lady will also get a 10% credit. Okay, and this will go on and on, right? Now, strategies can be of different types. For example, it is not that for every such referral, it is not that you will get this kind of referral bonus for every recommendation. You may get this bonus for the first recommendation, for example, right? The first recommendation that you make, you get this credit, and the other recommendation you will not get anything. It may also happen that you see, in certain cases, people say that, okay, in the first recommendation you get X amount of credit. In the second recommendation you get X by 2 credit. Third recommendation X by 4 credit, and so on and so forth. Right? So there was a very interesting study, where the data was collected from such an e-commerce service with around 16 million recommendations, around 4 million people, and around 500K products, right? And if you see the the curve, exposure curve, x-axis you see the number of recommendations received, and y-axis is the number of purchase. Meaning that x-axis indicates that I have received recommendations from 5 of my friends or 10 of my friends, and y-axis indicates that what is the probability that I will actually purchase that product. Okay, so this is exactly exposure curve. In the exposure curve, we have seen that x-axis is the number of exposures, and y-axis is the number of adoption. Here also exposure is number of recommendations, number of referrals, and y-axis is the x-axis is the number of referrals, and y-axis is the number of probability of purchase, right? So you see that here the curve looks very similar to the probabilistic model, where with the increase of this is increasing, right? But you see that this increase is not very consistent like this. Okay, after a certain time it remains almost constant. This is kind of a diminishing return type of setting, right? So and interestingly, if you look at the probability, right, in fact, with 40 recommendations, the probability is around 0.06, which is very less. This is interesting. What it is saying is that the growth, initially the growth is significant, right? Initially the growth is significant, but after a certain point, you give me whatever recommendations you want to give, but I would not be convinced, right? Or the convince or the probability is very less. Okay. Now this setting, this example, this particular data set was collected from an e-commerce service, and this was for a DVD kind of recommendation. right? So let's look at another type of recommendations where, there's a journal, there's a social media called Live Journal, okay, where you can essentially be a part of different group. Okay, so you see here in this particular example, this figure, okay, this circle indicates a particular group, okay, a social media group, okay, and red points are those points who are already part of the group, and yellow points are those points which are still not a part of the group, but they may they may want to be a part of this group, right? And people basically studied that what is the probability that a particular yellow node will join the group, given that say 6 of his friends or 10 of his friends have already joined the group, right? How does the probability of joining a group depends on the number of friends already in the group? If you, and this is again kind of an exposure adaptation kind of scenario, right? If you look at the curve here, the same thing, x-axis is the exposure and y-axis is the adaptation. Now, x-axis is the number of friends in the group, right? And y-axis is the probability of joining. You see the same kind of behavior, diminishing return type of behavior. Okay, you see here also, if you look at the probability, not that much. Okay, so the author has also mentioned one interesting point, which is this part. If you look at this part, the curve actually looks like this, something like this. You can think of it as an S-shaped curve. Okay, now this part is very important. What did it say is that initially the rate is not that high. Between 0 to 1, let's assume that this is 1. So between 0 to 1, the rate is not that high, but as you move away, right, your rate is increasing, the slope is increasing, right? So this is something that we need to understand. The author has not mentioned about the reason, but they noticed this fact, and they said that we may need to check the same kind of behavior for other kind of setting as well, whether it's really a diminishing return type of curve, or it looks like a S kind of shape, or something else, right? So now let's look at another interesting experiment, empirical experiment. So in this particular setting, right, Daniel Romero, right, they published a paper in 2011, and they wanted to understand the spread of different types of events. Okay, it can be a musical event, it can be something else, right? And they collected tweets related to those events, and they also and there are also users associated with the tweets. Okay, and they tried to understand exposure curve from a different point of view. Okay, this is the exposure curve. As you see, x-axis is exposure and y-axis is the probability of adoption, and they basically plotted this exposure curve for 500 hashtags. Okay, there are different events, there are different topics, and there are total 500 hashtags, right, including all the topics. And they plotted this, and they tried to understand the exposure curve behavior across different topics. Okay, so what are the questions that they ask? The first question they ask is that when a particular peak arises. Okay, now can we characterize the event based on the peak in the exposure curve, right? This is the first question. The second question is, how is the shape of this this particular curve, meaning that is it the case that the curve is first increasing, then suddenly decreasing, or it is increasing and then remain almost constant, or so on and so forth. Okay, so they defined two factors. One is called the persistence and other is called the stickiness. right? So using persistence and stickiness, they tried to characterize the exposure curve. What is persistence? Persistence is the ratio of the area under the curve P and the area. So this is P, right? Ratio of the area under the curve P and the area of the rectangle of the highest max P. Meaning that if this is the maximum value in the curve, right? You basically draw a rectangle, right? And you measure the area of the rectangle and you measure the area under this curve. Okay, and this is the ratio. So ratio in the numerator, this is this area under this curve, and the denominator, the numerator, this is the area, and the denominator is the area of this rectangle. Now think about it. Higher this ratio, higher the chance that the curve looks like this, right? So this is the first factor, persistent. The second factor is stickiness. Stickiness is the probability of the usage of the most effective exposure. Meaning, you just look at the peak. What is the maximum peak value? The most effective exposure. What's the maximum peak value? In this case, this is 0.02. Right? Now let's look at the experiments, right? So they have considered 1, 2, 3, 4, 5, 6, 7, 8. 8 categories, 8 topics: celebrity, music, game, political, idiom, sports, movies, and technology. And they collected associated hashtags, right? So each category has at least 20 hashtags, relevant hashtags, and total 500 hashtags, right? And then if you think of each category as an event, right? So for every event, you can draw this exposure curve, right? For every event, for every hashtag, you can draw, for every hashtag, you have a point, right? And you get this exposure curve. Okay. So from the exposure curve, let's first look at the persistence. Okay. So in this particular plot, y-axis, x-axis indicates different events, right? Political, idiom, music, etc. Let's look at the first event, which is political. Okay. And what is y-axis? Y-axis is the persistence value. What is persistence? Again, the ratio of the area under the curve and the area of the rectangle. Okay. Higher the ratio, higher the chance that that particular event has remained persistent, right, after a long time. Okay. So to understand whether things are really random or not, what they did, they also for every event they did some random randomized version of the experiment, right? The randomized version of the experiment, you just throw the particular hashtag randomly, and then again randomly somebody will adapt it, or it would not uniformly at random, somebody will adapt it or not, and so on and so forth. You make a random experiment for every event. So for every event, you have a random counterpart, and from random counterpart, you will get a persistence. You will again draw an exposure curve, and you can get a persistence value, right? That is basically these black points, right? You see that for every event, you have these black points. So the black point indicates the persistence of the random counterpart of that event. Okay, and this red line, red cross, indicates the actual persistence value obtained from the data. Okay, and this bar graph, you see this error graph. This error plot indicates so when you do random experiments, right, you have to repeat these experiments again and again, right? So you have different random settings for a particular event, right? So for each random setting, you have a persistent value. So you can get the mean persistent value across random events, and you can get the standard deviation. So this is the mean persistent value of the random event, and this is the standard deviation of the persistent values across random events. Okay. So, and then they repeated the same experiment for all the events. And they also plotted the actual persistence value. So you see that for events like political, right, sports, right, the actual persistent values are much higher than the random value. Even it doesn't fall within the standard deviation of the persistent value of the random counterpart, right? They are much higher than the random counterpart. Whereas events like, you know, technology, right here, events like game, right? So technology and game, here you see that, you know, the actual value, the actual persistent value is higher than the random part, mean random persistent value, but they actually fall within the standard deviation range. Okay, meaning that at least one such random setting has been able to capture the real event. Okay. On the other hand, events like idiom, music, the values are much lesser than the mean persistent value of the random part. Now think about it. Three cases. The first case, we have events like political and you know, political and sports. They have higher persistence value than the random experiment. Okay, meaning that for political and sports, the exposure curve looks like this. Okay, it is higher. It is, in fact, it tends to 1, meaning that the area under this curve and the area under the rectangle, right, they are kind of same. So these kind of events remain persistent, right? Political and sports, which is also evident, right? Okay. Whereas events like idiom, right, and music, I don't have idea about idioms, but let's take music, right? Now music, generally we have also seen that music, what happens is that, you know, it suddenly gets a peak and then it decreases. You know, it becomes viral within a very short period of time, then nobody cares about it until unless, you know, it's a award-winning music, right? Or a viral music, like whatever you know, right, what music I'm talking about these days. So until unless, you know, people, generally nobody cares about good music for a long period of time, right? It you know, it becomes popular in fragmented time period, but not very consistent. Whereas events like technology, you know, or games, right, celebrity, you see that, you know, these events are, you can if you draw random settings, you can be able to mimic the spread of this kind of hashtags. This is also quite evident if you think of it, you know, intuitively. Let's look at the stickiness. Okay, the same experiment happened again. Y-axis stickiness, x-axis events, random experiments, right? Here we have seen a different trend. Particularly look at the music, right? What I mentioned earlier, that music is not persistent, but music, the stickiness is maximum, meaning it is very clear that it looks like this, right? So events like music, celebrity, right, political, idioms, they have stickiness higher than the random part, right? Whereas technology, movie, right, here you see that, you know, this is lower than the random part, stickiness of the random part. Okay. So, there are other issues that I do not exactly, essentially want to mention here, because there are many other such empirical experiments done to understand the, spread of this kind of rumor or disease, right? So we have seen cases like SIR, SIS model, decision-based model. We have also seen something called reproductive number R0, and we mentioned that R0 is very important for a particular disease to spread, right? And we have seen probabilistic models like independent cascade model, and we see how independent cascade models can be simplified, where from ages probability you can move, you can map, you can assign probabilities to every nodes, and then you can draw something called exposure curve, and the exposure curve will basically characterize the spread of different types of information. Okay, with this I would like to stop here and conclude this chapter. Thanks.